Hello, in this video I'm going to solve the following problem for you. Let us read the problem together first. A hypothetical substance has an isothermal compressibility kappa equals to A over V and an expansivity beta equals to 2B times T over V, where A and B are constants. Of course, here T is the temperature and V is the molar volume. Part A. Show that the equation of a state is given by V minus B times T squared plus A times P equals a constant. Part B. If at a pressure P naught and temperature T naught, specific volume is V naught, evaluate the constant. That would be a good idea if you pause the video at this point and try to solve the problem yourself first. Okay, now let us solve the problem. First of all, let me tell you why these kappa and beta are important for us. Because the most important question regarding a system in thermodynamics is actually what the equation of a state for the substance for the system is. Yes, so if we can know what the equation of the state equation is for my system, then that's a good progress. And this is probably the most important piece of information that I need to know about my system. Okay, what an equation of a state is. An equation of a state is an equation of this form, a function of P, the pressure, the molar volume, and then temperature equals to 0. Okay, so you can imagine, of course, in principle, an equation of a state is a complicated equation, but the equation of a state is supposed to connect these variables of my thermodynamic system in any equilibrium state. Okay, so if I have a system in an equilibrium state in which P, V, and T are well defined, and then equation of a state is a relation between those quantities at any equilibrium state of my system. And of course, in principle, this equation can be solved for any one of these variables and express that variable in terms of the other two variables. For example, you can, in principle, think that I can solve P and express P in terms of V and T, solve for V and express V in terms of P and T, and solve for T and express T in terms of P and V. Okay, sometimes, of course, it is possible to do it explicitly if the state equation is simple. For example, for the ideal gas scenario, the equation of state is so simple that I can immediately express P in terms of V and T by dividing everything by V. I can express I can express V in terms of P and T by dividing by P, and I can express T in terms of P and V by dividing by R. So I can find an explicit relation so that every one of these quantities is related on the other two. But then most of the time, this is not possible, okay? So why these quantities are important? Because first of all, they are fairly easily measured in laboratory, okay? So I can find the relation for expressing kappa and beta. And after that, this will help, and a little bit of mathematics, of course, it will help us to find the equation of a state. So that is why kappa and beta in thermodynamics are important. So let us imagine that V is expressed in terms of P and T. Then, by multivariable calculus, I can say that dV is equal to the partial derivative of V with respect to the temperature when the pressure is kept constant, multiplied by dt, plus the partial derivative of V with respect to the pressure when the temperature is kept constant, multiplied by dP. Okay, and then now that was actually the motivation behind the definition of kappa and beta. Okay, so kappa is defined to be minus 1 over V, partial derivative of V with respect to the pressure when temperature is kept constant, and beta is defined to be 1 over V, partial derivative of V with respect to T when pressure is kept constant. Okay, so you see, this expression is exactly this one, and this expression is exactly that one. So from here, I can say that kappa V minus kappa V is equal to this partial derivative And from here, beta V is this partial derivative. Okay? So if I go back here, so this what I am talking about now is completely generic. So dV it is true for any system in any equilibrium state. So here, instead of that, I put this beta V, and then I have dt, and then instead of this expression, I put minus kappa V dP. And then I can divide everything by V, so I will get dV over V is equal to beta dt minus kappa dP, which is a generic formula in thermodynamics. Okay, now I use those pieces of information to solve my problem here. So instead of beta, I can put 2b times t over v. So let me write it here. So this is completely generic. Now I use the pieces of information provided for me in the problem. Instead of beta, I put 2b t over v dt minus, instead of kappa, I put a over b dp. And then I multiply everything by v. So this becomes dv is equal to 2bt dt. And then I will have minus a dp. So this is a relation between differentials dv, dt, and dp. But in order to find the equation of a state, I want a relation between p, v, and t themselves. Okay? So what should I do? I integrate. So I integrate dv. On the right-hand side, I integrate this one, but 2b is constant, so I have to integrate t dt, and then a is constant, integrating dp. Okay, but the integral, a primitive function for this integral of dv is just simply v. On the right-hand side, I have 2b, but a primitive function for t, when the t itself is the variable, is 1/2 t squared. 1/2 will cancel this 2, so I will have pt squared. And then finally, I have a integral of dp is just simply p. Okay, and then of course, I have a constant of integration. Okay, and then I move everything to the left, so it becomes minus bt squared plus ap is equal to a constant. So what was my goal? My goal was to find the equation of a state. What is the equation of a state? A relation among v, t, and p. So that's my relation. Of course, this one is so simple that you can also explicitly express v in terms of t and p. You can also easily express p in terms of t and b. And of course, if you want to express t in terms of v and p, you can do it, but you have to take the square root and taking care of plus minus signs that appears. Okay, so that's the first thing. But still, this constant is missing. So if I want to really understand my system by knowing its state equation, I also need to know C. So what we do, we prepare the system in an equilibrium state, and in that equilibrium state, we measure V, T, and P. So let us say those values for a particular equilibrium state are, as mentioned in the problem, V naught, T naught, and P naught. Okay? So it means that because this is valid for any equilibrium state, it is also valid for that particular equilibrium state. So it means that if I replace V with V naught, T with T naught, P with P naught, this equation should hold. And this will give me the value of C. So then it means that this constant C that I am looking is nothing except V naught minus BT naught squared and plus AP naught. Yes? So in principle, if you tell me what the equation of a state for this substance, hypothetical substance is, I would say that V minus BT squared plus AP is equal to V naught minus BT naught squared plus AP naught. So these are quantities for a reference equilibrium state, and the whole thing is an equation, is the equation of a state for my system. So that is a very nice problem because the mathematics involved in this problem was fairly simple. But the only thing that I want you to understand in this problem is why we are interested in knowing beta and kappa in the first place. So the simple answer is that because they will help us to find the equation of a state for the system under investigation. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.